Hello everyone and welcome in this new tutorial. Today we're going to keep discussing about WebGPU and we'll be focusing this time on the reduction algorithms. Last time, if you remember, we described how you can set up the support for the timestamp queries in a native WebGPU, and the idea now is I'm going actually to use this query mechanism to try to monitor the performances of some different version of the reduction algorithm. And in any case, I want to keep this recording pretty short again, so it's only going to be the beginning of it. There will probably be second recording and maybe even the third one. I'm not sure. We'll see how this goes. But anyway, let's get started now. First, in case you're not really sure what reduction is, let's just discuss a little bit about that. The idea is really that you would start with an array of values, like this one for instance, and then you're going to try to compute the sum of all the values together. So yeah, if you have 8 slots like in this case and you have the value 1 in every slot, then the result that you should get when you run your reduction should be 8. But you're not, of course, limited to setting the value to just 1 or maybe just 0 or something like that. You can put whatever you want in those slots. So you can have, for instance, an array like this one, and if you do the computation here, you get 1 plus 4, that's 5, 6, 7, then 10, then 12, then 13. So the result in this case should be 13. The problem here is, yeah, I'm using a very simple array here with only 8 elements, but you have to imagine that in realistic projection scenarios you will be trying to run reductions on much more bigger arrays, and it's in fact a bit of a problem if you try to run this on your GPU, because the GPUs are very good at running a lot of stuff in parallel, but when you have to do a reduction process, you're actually not really running everything in parallel anymore, because you have dependency between all the values and you need to compute the sum going through all the values. So this is some kind of what we call a scan operation. So you go through all the values this way, and you have to be careful on how you're going to optimize that on your GPU. At least that's the big picture, and that's how I see it myself. Maybe I'm missing some details, but you can still look for additional information on this. So let's continue maybe with a few words on how we're going to test those implementation. First, as you might expect, we're going to write those reduction algorithm using a compute shader every time. And the idea is I'm going to prepare some unit tests to verify that the shader is doing what it's supposed to do, and then we're going to try to monitor also the performances for this shader. And we are going to start in every cases with a simple array of unsigned int value inside int32 values. And in fact, in my case, in every slot, I'm only putting value that are between 0 and 4, as far as I remember. And the idea then will be, again, to try to sum all those values together to produce some result on the GPU. What you can do when you have generated that in your unit test is that you can already compute the sum of all the values on the CPU side. So this is the reference result that you would like to produce on the GPU side. Then what we do is we take this array and we're going to upload that on the GPU as a storage buffer. And this storage buffer is actually going to be read-only. You don't need to write anything in this. This will be one of the two inputs that you're providing to your compute shader. The second input that you're going to provide is another storage buffer, which will be in fact just a single unsigned value But this time you will have support to write into the storage buffer, because the compute shader is going to do its thing with all the inputs, and at the end it's going to write an output into this storage buffer. Once you've done that, you can, as usual, download the data from the storage buffer on the CPU side, and then when you have the CPU reference value and the output of your shader, you can of course compare the two values, and this will tell you if the unit test is passing or not. The nice thing that you can do at the same time is, on this part, in fact, you are going to submit a few commands to your GPU with WebGPU, and we're going to first request to write the timestamps at the start time, and then you're going to execute this compute shader. In fact, we're going to execute that a few times in a row, and after that we're going to write the final timestamp. So in the end you get those two timestamps, and you can compute the time that it took to execute the compute shader. That's how you can in fact then figure out what is the performances for your shader, because you're basically injecting a large array of integer value here. So typically what I'm using is 2 to the power 22, so that's something like 4 million something. So you're going to process those 4 million integer value in the time that is computed here between timestamp 0 and timestamp 1. And with that you get the notion of bandwidth, so you know that you are able to process that much gigabyte of data per second. So yeah, this would be our reference. And I guess it's a good idea maybe if we have a look now at the unit test itself. So we have this reduction spec file, and in fact we already mentioned that in the previous recording when I was discussing the timestamp generation. And what we do here is what I just described before. We're going to generate a random array for the input. The number of elements that we have is this 4,100,000 and blah 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 so on. So that's the first buffer that you're going to provide, but you're also providing an output buffer where you're going to write the result from the compute shader. And then we have a number of iteration. We compute the total value that we have in your input, and you multiply that by iteration and +1 in fact, because I'm also still modifying a few things here due to the fact that the timing result that I'm getting are not very precise. And I was thinking maybe it was due to the fact that I was taking the compilation of the pipeline also into account in this time. So I decided to add a dry run here. We're going to take the compute path and execute that once, not trying to measure anything from a time perspective. And only after that we will start monitoring the time and execute the compute path again multiple times. Unfortunately, this didn't really help, and I still get weird results when I'm trying to measure some time values. But never mind. So yeah, we're going to execute this compute path and measure the timestamps from the start to the finish. And in the end, you have to read the value back, so that's the output where you have written the integer value, which is the sum of all the values. And when you read this, you can compare that to the expected total value, and this will tell you if your implementation in the shader is right or if you messed something up. And yeah, this is it basically. And now we're going to get another view on 3 different versions of this reduction shader. The first one, which is reduc 0 here, is what I call the naive implementation here. I was just thinking, okay, if you have an array with multiple values, what would be a simple way to compute the sum of all the values? The most simple way is to do it sequentially, like you would do on the CPU side. You would go with a for loop and iterate on each element and add that to the total value. So this is exactly what I try to do here. Of course, this is a very bad implementation on the GPU because we have to read the value from the device memory, then you add that to the output, which is again on the device memory, and you have to do that using the atomic addition process because multiple threads could be trying to add their value to the same output. So you definitely want to do this atomically. And anyway, the results were not very good, but not that bad either. So you get like 164 gigabytes per second. Knowing that the test that I'm running that with a RTX 3090, and the theoretical max bandwidth that you have for the memory is something like 936 gigabytes per second. So yeah, pretty far from the limit, of course, but that's a start, that's a reference point, and we'll see how we can improve further on that. So if we have a look at the shader itself, Redux 0, the implementation is very small and very minimal. First, you need to provide the two buffers that I mentioned. You have first the input buffer, of course, so that's the read-only array. And you have the output buffer, which is just a single integer value. And we have to consider this is an atomic on an unsigned integer for WebGPU, because WebGPU is very strict, and if you don't specify that this is an atomic, you're not going to be able to write to it here. And what we do next is we are provided with the global invocation ID. Of course, it's a vec3 normally, so you have the X, Y, and Z components. But then depending on how you set up your compute grid, you may, like we're doing in this case, only consider that we have values on the x-axis, and y and z are both set to 1, or I mean the size is 1. So yeah, we're just checking if the ID is still inside the bounds of the input memory. In theory, it should not be necessary here because the workgroup grid is going to execute a few work groups, and you will actually stop exactly at this limit value. So, but anyway, in the generic case, you probably want to include this kind of check. So yeah, this is it, and you're going to just accumulate your value at that. And next, after that, we are going to move to the Nvidia reduction kernel implementation themselves. What I just noted at the top here, but I have not mentioned yet, is that the whole idea here is really to use this Nvidia reduction optimization paper. So we can just have a look at this one. It's the optimizing parallel reduction in CUDA. And that's actually where I found everything concerning how you can improve the performances for your reduction algorithm. And now, yeah, let's start with the first implementation. So the kernel number 1, where is this? It's this one, the interleave addressing. So that's how you would implement the reduction shader, or reduction kernel in this case, with CUDA. And what we're going to do is try to use that as a reference and modify the syntax to get this working with WebGPU WGSL language. The very nice thing that we have with those kernels here is that now we're going to start using this shared memory, which is definitely what you want to do to avoid accessing the device memory constantly. So here is the implementation corresponding to this kernel number 1 in WGSL. We're going to use those same inputs again as in the version 0 here. And then, yeah, this is an adaptation of what we had in the Nvidia paper. The first part here concerning the shared data. On CUDA, you would define that inside your kernel itself, But in WebGPU, this has to be an external variable, like here. Apart from that, on CUDA here, we see that we're going to compute the global index. So you're going to use the block dimension. Block dimension is on WebGPU side the workgroup size, and the block ID is the current workgroup, and the thread ID here is the local ID in WebGPU. What we were providing in this version 1 is already the global invocation index, so we don't really need to compute that, but we can in fact compute that from the current workgroup ID and the local invocation ID, which we have here. So another thing which is different, of course, is here we have this workgroup bar here, and that's the same thing as the sync thread here in the CUDA. And apart from that, really the logic stays exactly the same. So here we're going to retrieve the data that we want as input from the global memory and store that in the shared array, and that's exactly what we do on the WebGPU side. We're going to store in the shared array the input data, and we have this check again on the out of bounds condition, but again it should really not be needed here. And after that, we're going to synchronize all the threads in this workgroup. Then we're going to run this for loop here, synchronizing all the threads at the end of every single step. And again, this is the same thing that we're doing here on the WebGPU side. And at the end, if you are on the thread number 0, the local thread 0, that's where you're going to take the output of your reduction, which is normally available in the first slot of your shared array, and you're going to add that into your output destination. This means that in this case, for instance, if I have a workgroup size of 256, then I'm going to use the shared memory to compute the sum value of 256 input values before I write a single result in the in this output value here. So you effectively reducing by 256 the number of atomic addition that you're performing here, compared to the original reference version that we have mentioned before. So you could expect that the performances would be much better, and in fact, no, they are actually worse. And yeah, I can't really explain the details myself, but from what you can read on the paper here, it seems that the problem here is in this for loop. First, the warps are going to diverge. Not quite sure what this means exactly. I guess it means that you have different behavior for consecutive threads in a warp. So not so good. You have to execute the threads sequentially in this case. And also the modulo operator is apparently very slow. So yeah, I guess this is all the explanation that we can have here. And this produced, as I said, pretty bad result, because in the first naive implementation we had 164 gigabyte per second, and we only have 155 gigabyte here. So not so good. But anyway, we continue then further with the next reduction kernel number 2 in the Nvidia paper. But in fact, I did not implement that. I was a bit lazy, I guess, so I moved directly to the version 3. But still, in the paper, what they mentioned about this version is that you're going to introduce stride index and non-divergent branches in this case. So you can maybe just have a look at what it is exactly. Yep, we're just replacing this for loop here with something like that. And that would be enough in theory to improve your performances by a factor of 2.3. So pretty large increment already. But yeah, this is also introducing another problem now with memory bank conflicts. So yeah, this is another major issue that you have to be aware of when dealing with shared memory. Those bank conflicts is something that will reduce the performances of the shader. If, for instance, you have a shared memory array and you store something in the slot 0 of that array and something else in the slot 32 if you are using simple integer 32 values. So in this case, you have a bank conflict. Probably want to check for other source of information on that, but in the end, it's not that tricky to understand. Those banks are really consecutive 32-bit slots, and if you try to access slot 1 and slot 16, they're both the same. So you can't do that. I mean, you can do that, but it's going to serialize your access to the memory, and that's reducing the performances. Okay, that's too complex. Never mind. So yeah, let's move to the version 3 now. Version 3 was an introduction of the sequential addressing process. So you're going to collect all the values, but sequentially like that. So this is in fact resolving the issue with bank conflict, and this is what I have implemented myself. So the version number 3 reduction here, and if you compare that to version 1, you will see that the differences are pretty minimal. In fact, what we have is that we're going now to use the workgroup ID and the local thread ID. Why exactly, I'm wondering. We could still keep using the global ID in this case, but yeah, I did the change anyway. And when you have your workgroup ID, you use the workgroup size and the local thread to figure out what is your global ID. Then again, you are going to populate your shared array with the value that you read from your global input. And next, what is different is this loop. Then we have this difference on how you're going to iterate on the loop, and here the check that you're going to use and the index that you're going to use to access the shared data are also different. And this is again going to improve your performances quite a lot. So at the end, with this you get more than, usually you get more than 216 gigabytes per second. So a pretty good improvement compared to the, well, not so good version 1, and even compared to the naive implementation. But in fact, we can keep going and do much more than that. And this will definitely be for the next recording, because as I said, we need to keep those tutorial pretty small. So yeah, we'll keep discussing about that in the next video. Meanwhile, if you have a question on one of those version already, just let me know in the comments as usual, and otherwise I'll see you next time. Bye bye.